Welcome back, guys. In the previous video we classified solid into conductors, insulators and semiconductors based on their electrical resistivity. But why such difference in resistivity or conductivity occurs? To understand these differences in electrical properties, we need to know about the nature of energy bands. From Bohr's atomic model, we know that an isolated atom has a finite energy level corresponding to different cells and subcells. And when two atoms come close to each other, there is an interaction between the valence electrons of these two atoms. And the Pauli's exclusion principle, which states no two electrons in a single atom can have the same value for all the four quantum numbers, comes into play and prohibits the two electrons from having the same quantum state. So this interaction causes a splitting of each individual energy level into two slightly different energy levels. When large number of such atoms get together to form a solid, these individual energy levels overlap and get completely modified. Imagine that this is energy level of a single atom, and now another atom comes whose energy level is this, and similarly several atoms come together and their energy levels starts overlapping with each other, and we get a continuous band. Now instead of discrete values of energy of electrons, the energy values lie in a certain range. The collection of these closely packed energy levels are said to form an energy band. Now let's have a closer look as to how bands are formed. For that, consider a silicon atom whose atomic number is 14, and if we write it electronic configuration, we can write it as 1s2, 2s2, 2p6, 3s2 and 3p2. We know that p orbital has 6 subcells, but here we have only 2 electrons, so that means 2 subcells are filled and 4 subcells are empty. Now if you consider a silicon crystal having n atoms, there will be 14 n electrons, and in 3p energy level only 2 n states are filled and 4 n states are empty or unfilled. If we plot the energy of electron against the interatomic distance r, it will look somewhat like this. Now we'll discuss the following 4 cases. When the distance between the two atoms is d3, or when the interatomic spacing is very large, each atom in the crystal behaves independently and they do not influence each other, so they have discrete energy states. Now let us decrease the distance to d2. Now in this case, the interaction among the valence electrons splits the 3s and 3p levels into a large number of closely spaced energy levels. As you can see here, this is 3p getting splitted, this is 3s getting splitted, and the energy of an electron may be slightly more or less than the energy of an electron in a single atom. So corresponding to the states 3s and 3p, two bands are formed. Now let us further decrease the distance to d1. In this case, the 3s and 3p bands overlap, as you can see here, they are overlapping, and since they are overlapping, the energy gap between them disappears. Now all the A10 levels in the electronic configuration of silicon, in the outer subshell we have 3s and 3p. So here we have 2n and 2n filled states plus 4n unfilled states, which is equal to 18 levels or states in total. And these 18 levels are now continuously distributed, having 4n energy levels filled and 4n empty. If we further decrease the distance to a, that is the equilibrium separation, meaning the two atoms cannot come closer than this. The filled and unfilled energy levels are separated by an energy gap called forbidden energy gap, represented here in this graph by Eg. And the band formed by filled energy levels is known as valence band, whereas partially filled or unfilled band is known as conduction band. Now, depending upon the size of this energy gap, different materials behave as conductors, semiconductors, or insulators. Now, let us have a look at the energy bands in insulators, conductors, and semiconductors. Now, in an insulator, at absolute zero, the valence band is completely filled and the conduction band is empty. And the forbidden gap between the valence band and the conduction band is quite large. It's of the order of 6 electron volts. Now, even if we excite the electrons in the valence band, they will not have sufficient energy to jump over to the conduction band, and therefore insulators cannot conduct electric current. Now, in case of a conductor at absolute zero, there may be two situations. The first one, the conduction band is partly filled and the valence band is completely filled. Now, this happens, for example, in case of copper. And the second case, the valence band is completely filled and it overlaps with the conduction band. Now, in both the two cases, there are available states for electrons to move about. And since the gap between the energy levels is infinitesimally small, the electrons can easily move to the higher energy states, and these electrons act as the charge carriers in the conductor. And these electrons are called conduction electrons or free electrons. And in case of semiconductor at absolute zero, the valence band is completely filled and the conduction band is completely empty. Hence, at absolute zero or at very low temperatures, semiconductor is an insulator. The forbidden gap between the valence band and the conduction band is very narrow for semiconductors. It is approximately of the order of 1 electron volt. For example, for germanium, the forbidden gap is equals to 0.75 electron volt, and for silicon it's equal to 1.12 electron volt. So that's it for today, guys. See you in the next lecture.